Hello everyone. We had seen some problems or some questions about how to do building of Z bus. Two methods. One method was inverting Y bus, and the other method was building the Z bus step by step. And I had given you some algorithm uh, in one of my previous videos about how to build a Z bus. And in that algorithm, we had identified these four cases, and I did not show you any derivation how this thing is done. So in this video, I would like to show you the derivation. So I had only shown you how you use these four uh, cases to build a Z bus, but then how this from where does this formulas come from, and then how these cases come about, all these things we are going to do it in this. Now I also know that there's an exam coming up for the students who are taking this course, and some of you might have a doubt, will the derivation be asked in the exam? And let me right away tell that, those who are worried about the exam, this derivation I will not be asking in the exam. So this video completely, whatever you are seeing, this is optional. So if you are interested, this is a nice mathematical discussion in this video that is going on. It will be interesting. Mathematical manipulation of a lot of matrices we are going to do, and and finally, as a result, we get these four cases that are shown on the screen right now. So this is derivation. So you are interested, you go through it. Otherwise, it is optional. You don't have to go through this. It will not be asked in the exam. Maybe you are preparing for the exam. You practice more problems, uh, and then later on after the exam, you can come back to this video and actually learn. What is the derivation, how it is. This is coming. Okay. So with that brief introduction, so let me start explaining about this, how the bus impedance matrix is derived. So I'll go to a fresh page. So what I'll do now here is, even before we go to working on our power system matrices, we'll just work on a generalized matrix. That is, we'll work on matrix A and see what is known as Kron's reduction. So this is a mathematical manipulation technique. So given set of equations, so let me write the question actually, something like this: 3x plus 4y plus 7z equal to, this is 7, and 1x plus 8y plus 9z equal to 10, and then maybe 5x minus 4y minus 2z equal to 6. So I'm just making this up, three unknowns, three variables. So now the question is, I'm sorry, this is not 6, this is actually 0. The question is, given the set of equations, okay, and given that one of the right hand side elements is 0, so can you eliminate one variable? So if I write it in a matrix form, so this is the question: how do you eliminate this one variable? So eliminating one variable is called reduction. So you are reducing from three variables to only two variables. That is why it is called reduction. In other words, let me write it slightly in a mathematical form. This I can write it like this: 3, 4, 7, 1, 8, 9, and then 5 minus 4 and minus 2. So this is, I'm getting from this, and then if I multiply it with x, y and z, then I have 3, 10 and 0. So the fact that this is 0 is interesting, and that is you required for applying the Kron's reduction. If it, instead of 0 it is plus 1 or minus 1 or 8 or whatever, any other non-zero number here, you cannot apply Kron's reduction. Kron's reduction only can be applied where there is a 0. Now let's say I want to eliminate z, I want to make it only x and y. So from this, I want to get some other matrix, don't know what matrix is that, some other matrix multiplied by x and y, and I should get, maybe this also will change, I should get this kind of an equation. So let's see how this, so here the size is 3 cross 3, here the size will be 2 cross 2. So this is the Kron's reduction. So what you do is this, just look at the last equation once again here. So from this last equation, what do you infer? Can you find out what is z here? So z is nothing but 5x minus 4y divided by 2. So from the last equation, let me write down 5x minus 4y minus 2z equal to 0. This is the last equation. From this, I'll get z equal to 5x minus 4y divided by 2. So that minus also will get cancelled when this goes to the other side. Now look at the first two equations. So what is the first equation? 3x plus 4y plus 7z. 3x plus 4y plus 7z equal to 3. Now in the place of z, I can substitute this one. So I get 3x plus 4y plus 7 by 2 into 5x minus 4y, then that is equal to 3. Now this is only in terms of x and y. So I can write 3 plus 7 by 2 into 5, this whole thing into x, plus 4 minus 7 by 2 into 4. So this minus will get multiplied. So this whole thing into y equal to 3. So this is 35 by 2 plus 3. So 35 by 2 plus 3. And then this is 28 by 2. Or I can cancel 2 2s are 4. 14. 4 minus 14 is minus 10. So minus 10. So first equation I got it like this. So similarly now take the second equation, that is 1x plus 8y plus 9z equal to 10. So second equation, 1x plus 8y plus 9z equal to 10. So this, I know this, what is the value of z. So this I can substitute here. Then I'll get 1x plus 8y plus 9 by 2 into 5x minus 4y equal to 10 again. So again here you see it is in terms of x and y. So 1 plus 45 by 2 into x plus 8 minus 9 into 4 is 36. 36 by 2 equal to 10 into y. So this goes 18 times and this is again minus 10y. So whereas this term is something different. So this is again minus 10y, but then here it is 1 plus 45 by 2 equal to, this is 10 again, right? So now you see from 3 variables I reduced to only 2 variables. This reduction is possible because we took advantage of the 0 that is present here. And this process, whatever I have done here, this process is called Kron's reduction. So this is the first equation. So from the equation, third equation, I have written z equal to something and then all these things. So I hope you understood this procedure, because we are going to use Kron's reduction in building z bus. So that's why we are discussing this mathematical thing here. So let's do it in terms of matrices. So I have done in terms of by writing individual equations, but then if there is a generalized, this is only a 3-bus system. So if there is a generalized way, so for example, I have ax equal to b. So where the size of a is something like a11, a12, so on up to a1n. Similarly, second row A21, A22, so on up to A2n, and so on up to AN1, AN2, so on up to ANN. So I have this n cross n matrix. This is multiplied by x1, x2, so on up to xn. Then I'll get something like this: b1, b2, b3, so on up to bn, where bn equal to 0. This is a special case. So, question: if bn equal to 0, then eliminate xn. So I want to write it in the matrix language, the whole procedure. So how to eliminate xn in this? So what you do is take this A matrix and then write it in this form. Basically we are splitting the A matrix. So what I'll do is I'll write it as A dash. And then I'm making basically it's just A itself, but then A dash will be the n minus 1 by n minus 1. So the first n minus 1 rows and first n minus 1 columns I'll be having. And whereas this one will be a nth column and this will be a nth row and this will be the ann element. So this one, if I multiply xn up to xn minus 1 and then xn is the last one. This is nothing but b1 up to bn minus 1 and finally bn itself is 0. So now if I look at this, if I only write the first n rows, I'm not interested in the last row, just I'm interested only in the first n rows. So what I'll get it. So focus on n minus 1 rows. So if I only focus on first n minus 1 rows, then from this I'll get a dash and then an column multiplied by x1 to xn minus 1 and then xn is equal to this one, b1 to bn minus 1. So I'm just writing only the first n minus 1. Last equation I am not writing. So let's just quickly confirm this rows. So how many rows are there in this? N minus 1 rows. But how many columns are there in this? So all n columns are there. Whereas here, how many columns are there? So there is only, so there are n rows and then one column. And here also we have n minus 1 rows and one column. So if you multiply these two matrices, this n will get cancelled and then n minus 1 cross 1 will be your output. So the dimensions of the matrices are agreeing upon. Now this one I'll slightly rewrite again. So I'll rewrite like this. I'll write it as a dash multiplied by x1 to xn minus 1 plus this I'll separate it, an column multiplied with xn is equal to b1 to bn minus 1. So do you see how this comes from this? I split this matrix into two parts. So again, let's check with the dimensions. Now this is n minus 1 cross n minus 1. This is n minus 1 cross 1. This is only the last column, but then n minus 1 rows. So n minus 1 rows by one column, and this is anyway a constant. Finally, you will get this size. Now let's call this as equation A. Now I go back and then look at only the last equation, last row. Now focus on the last row. So if I focus only on the last row, then I have nth row, an row multiplied by this, an multiplied by xn will be equal to 0. So I'll get like that. So that is an row, the nth row multiplied by x1 to xn minus 1, and then plus ann into xn equal to 0. So from this what is xn? So if I want to find xn, so first I'll take it to the other side. So minus ann xn equal to this entire thing, that is an row x1 to xn minus 1, and then finally here uh, this ann will become 1 by ann here. Since it is a constant, of course minus will also be. Since this ann is just a scalar single number, so it's not a matrix actually, it's a 1 cross 1. So I can write like this. So again, this is n minus 1 rows into one column. This is one row into n minus 1 column. So if I multiply these two matrices, this cancel out one by one, and then this one will get it, and which is nothing but xn. So this, let's call it as equation B. And notice now equation B I can substitute in equation A. So because for the value of xn. So if I do that, then I'll get it something like this. I'll get a dash. So this I can factor out actually. So I have this I can factor out. Then I have minus 1 by ann. Then I have so this minus 1 by ann is constant, so I have just taken it outside. So an column multiplied by an row, all of this entirely is multiplied by xn to xn minus 1. So this is will be equal to b1 to bn minus 1. Now if you look at the dimensions, this is n minus 1 cross 1, and this one is n minus 1 cross n minus 1, because this is n minus 1 cross n minus 1. This is n minus 1 rows into one column. This is one column into n minus 1 rows. So therefore finally everything will become n minus 1 cross n minus. And this one is the new matrix. So what is the Kron's reduction? So simply take a dash. From that a dash you subtract 1 by ann and then multiply an column and multiply an row. So this process will give you a reduced matrix. A reduced equal to this. So this is very important formula for Kron's reduction. So let's apply it to our formula, our earlier problem. So what's our earlier problem? If I go up, our earlier problem is this. So I'll just take this problem. So let's solve the following. Solve in the sense apply Kron's reduction. So from this, what is a dash? So A dash is nothing but this matrix. So 3, 4, 1, 8. What is ANN? So ANN is nothing but minus 2. And what is AN column? Nothing but nth column of A. That is 7 and 9. And finally, what is AN row? That is nothing but 5 and minus 4. So I have all the ingredients. So from all these things, I can find out the reduced A matrix. So A reduced equal to, so this one. So 3, 4, 1, 8 minus 1 by minus 2 multiplied by 7, 9 multiplied by 5 minus 4, and that's it. So again, let me take help of MATLAB to do this. So I'll go to a new file. So here I'll define AD equal to 3418. 3, 4 is first row, 1, 8 is the second row. Next, 1 by minus 2. So ANN is minus 2. Then AN column equal to AN row equal to. So what is my column? 7, 9. So 7, next line 9. And what is my row? 5 minus 4. So this is 5 and this is minus 4. So this is a row matrix. Now I have everything. So A reduced equal to A dash minus 1 divided by ANN multiplied by AN underscore call multiplied by AN underscore row. So if I do this, then I'll get the A reduced matrix. So let me just run it now. So here I'm getting A reduced matrix 20.5 minus 10, 23.5 minus 10. So this is nothing but 20.5 minus 10, 23.5 minus 10. This is my A reduced matrix. And then finally writing it back in the form of equations. So I'll get it. Therefore, this multiplied by xy should be equal to this 310. So these numbers we can also confirm from the previous example, like individual manual or equation oriented solution that we got before. So here we have it. 35 by 2 is 17 and a half. 17 and a half plus 3 is 20.5. So I'm getting 20.5. And this one is minus 10. 45 by 2 is 22.5 and plus 1 will be 23.5, and then here I'll get minus 10. So into xy equal to minus 3. So the answer, so note, solution by equation substitution and Kron's reduction formula match. Like they are matching because it is math. Anyway, so let's go up. So this is our important take uh, take home from this. This formula will be useful whenever you face a matrix like this, and then one of the element is 0 and you want to reduce the size of the matrix. We can use this. Now taking help of this, we are going to do. So this is like one stage of this video. So let's go further, take some more steps in this, and then we'll try to complete that. So I'm going to a fresh page. Now let's actually start discussing about the different cases. So let me get the cases once again here. So these are my cases. So I'll copy this. All right, so we are here. So case one is that a new line is added. So Z bus is nothing but just the first element itself. But what if there is already an existing Z bus? So let me explain that. So case one derivation. So there is already a Z bus, and the case is a new bus is there. So let's call that as bus K, and that new bus is having there's a line of ZB impedance added to the ground bus. In that case, what happens? So what is the equation for this one, for the original Z bus? So we have current injections is nothing but Z bus multiplied by V bus. So this will be I1, I2, I3 up to IN, whereas this one will be N cross N matrix, and then this one will be V1, V2 up to Vn. Now because I am introducing a new bus bar, so the size of the system will increase. So size will increase. So I have I, and the last element is actually this current IK. So IK current is one additional current that is entering into the system, and the this current is not disturbing the regular Z bus. So Z bus will also have different bus bars here. So n number of bus bars are already there. So that part anyway it will be same. So the Z bus will be same for the earlier part. It is also not disturbing the voltages of these bus bars. So V1 to Vn will be as it is. Now because of this new, so just simply use Ohm's law. Ik into Zb is nothing but Vk. So because this side is 0, so Vk voltage is nothing but Ik multiplied by Zb. So I should use Zb here. I'm sorry, I made a mistake. This is actually V and this is I. So I got habituated of writing Y bus. So V1, V2 up to Vn, and then I1, I2 up to In. So this also V1 up to, here last one is Vk, and here last one will be Ik. So this will be I1 to In. So let me just, sorry to confuse you. Let me just write here I1 to In, and last one is Ik. And Ik into Zb will be Vk. So therefore, by definition, these things all should be zeros. So this is the new bus, and this is not actually nothing but case 1. So in case 1, what we are doing is adding a new bus to the reference. So in that case, just simply increase the size of the Z bus by 1, keep the old Z bus as it is, and then just add one new element, and the column and row should be zeros. Okay, this is the case 1. All right. Now let's do case 2. So what is case 2? Case 2 is a new line or a line added to existing bus. So let me draw the diagram. So this is the Z bus. This is the reference. And one of the buses, let's call it as bus K. To this bus K, external current used to be IK. Now apart from that IK, a new bus is added. Let's call this as Q. So this having a current injection of IQ is added, and this impedance is ZQ. or ZB. Let's be consistent. So how will the system equations change? So what you have here is this is a new bus VQ and this is an old bus VK. So only thing that is changing, if I simply cover this part is completely covered, only thing that is changing is that, like, let's say if I completely ignore this part, then only thing that is changing is that an additional current of IQ is entering into VK bus. So I'll just put this back. So therefore we have V1 up to Vn. Of course, in between there is a Vk also. This one, how will it change? So it will change in this way. So this is Z bus. So the current injections are I1. At the place of IK, I will have additional current of IQ and then finally IN. So this is how it will change. Now you notice, if you just look at only the VK, so what is the effect of adding this IQ? So this IQ or this term is all the time multiplying with only the kth column of the Z bus. Because it is in the kth row, it will multiply with the kth column of the Z bus. So that is the effect of adding this. So what I will do is, I'll just continue it same like this, V1 up to Vk up to Vn here. And here I'll just take the Z bus. To that I will add one additional column, Zk column. The kth column of the Z bus I'll add it like this. And this side I have now subtracted, so I separated. So I1 to Ik, and then finally I'll increase the size. So this is In. I'll add one more IQ at the bottom. So because I increased one column, I am increasing one row here, so that the multiplication would be possible. So this is how the first n equations will change. Now also look at, now we'll go back to the new bus VQ. So what is the relation between these two? So VQ minus VK, the potential difference, is nothing but ZB into IQ, like this. So, or in other words, VQ is nothing but VK plus ZB into IQ. So I have this interesting equation. So therefore, if I add VQ to this as another additional row, then so this anyway another additional row is added in IQ also. So here I will be getting, so what is VQ? VQ is nothing but VK plus IQ into ZB. Now what is VK itself? Look at this. What is VK from this? So what is VK from this is ZK row. So the kth row of Z bus, so from here to here, is getting multiplied with I1 to IN. I1 to IN. Plus this last element will be kth row of kth column. So that means it will be ZKK. So that is multiplying with IQ. So this whole thing is actually VK. And to this, I am adding ZB into IQ. So finally what happens? So this is nothing but ZK row plus I'll add this element ZKK plus ZB into I1 to IN, and finally IQ is also added here. So now this is VQ. So now I can always add this term here. So from here I'll go here. So I'll just, by adding this, I'll get zk row, and then here zkk plus zb. So this is the final manipulation that we are doing. And the size of the system will increase because after all we are adding a new bus to the existing bus. So finally this is the formula for case 2. And this formula for case 2 is actually same what we had written. So if I go up, so look at this case 2. So what I'm doing, I'm taking the old Z bus, copying the kth column and copying the kth row, and then ZB plus ZKK, I'm just adding it into this corner element. That is how I'm updating the Z bus. So as simple as that. Now let's use case 3. Let's go to case 3 now. In case 3, what is happening is there is already a Z bus. Then there is a bus K. That bus K is actually connected to the ground bus. So an existing bus is connecting to the ground bus. So basically it's like adding a shunt element to the Z bus. So I want to add a shunt element to the Z bus. So what happens? So first here again we'll do a very cute mathematical trick. So just imagine that this switch is open, and then there is a new bus VQ here. So now what is the case? It is just like case 2. With the switch open, it is just like a case 2. So what we'll do? So first I'll apply case 2. With switch open, I'll apply case 2. So case 2 is applied within case 3. So what do we get? Z bus equal to old Z bus. So this is Z bus new equal to Z bus old. To this old Z bus, what is happening? ZK row is copied, kth row. ZK column is copied, and then here ZKK plus ZB is copied. So this is how the system is changing. So this is Z bus new. So let me move this Z bus new. So this is my Z bus new. So, and what is on the left hand side and what is on the right hand side? So here I have V1 up to Vn and a new voltage Vq added at the end. Similarly here I have I1 up to In and a new current Iq that is coming here. So now I close the switch. So when you suddenly close the switch, what is happening? Vq is becoming 0. So therefore this term will become 0 with switch closed. And now I can apply Kron's reduction. Already the things are made out for me. When this is 0, how to reduce this thing? So Z bus new is equal to Z bus old minus of 1 by ZKK plus ZB multiplied by ZK column multiplied by ZK row. So this is just applying the Kron's reduction formula. This is for case 3. So again, if I go up and then verify what is there for case 3, so I have Z new equal to Z bus old minus 1 by ZB into ZKK, kth column and kth row. This is exactly the same formula we had derived. Now, finally, one more thing left for us to derive. That is what happens when a bus is added between the two buses J and K, when a new line is added between them. So, again, let's do that. So, this is the last case, so you have to simply be a little bit patient with this. New line added between old buses J and K. So, what will be the diagram for this? So the diagram for this will will look something like this. I have existing Z bus, so let me draw it a slightly bigger one. This is zero node, and this is the Z bus of the system. In that, I'll identify two nodes. This is node J, and this is node K. Now, node J used to have injected current IJ before, and then this also used to have injected current IK before. Now, additionally, I am connecting a line like this. And then I am assuming, so this is ZB, and I am assuming a new current IB is flowing like this. So what is the now the new current injection at J? So the current injection at J, earlier it used to be only IJ, now IB is also added. Similarly, new current injection at K will be, earlier it used to be IK, but IB is subtracted from that. So this is the change in the current injections. Now these current injections, how will it change the voltages? That is what is our question next we are asking. So V1 to Vn. So of course in between there will be, let's say, Vj and then Vk and finally Vn I have. So this is the vector of voltages. So this is the old Z bus. Z bus is not changing right away here. We are not showing the change right away here. What we are now doing is like this. I1. Now at Ij, I am adding Ib. Similarly, at Ik, I am subtracting Ib, and then that's it, In. So this is how it will change. Now, what is the next step? The next step, if you look from this, will be this term. When I actually do the matrix multiplication, what is happening with this plus IB? The plus IB is all the time getting multiplied with the jth column of the Z bus because it is at the jth row of the this element. So the jth column elements will get multiplied by plus IB. Kth column elements will get multiplied by minus IB. So I can actually split this vector like this. So V1 to Vn is equal to, I can have the same Z bus with one additional column at the end. And this additional column is Zj minus K column. That means I'll take the jth column. From the jth column, I'll subtract the kth column. The subtraction, all that items or elements, I'll just keep it in this. Now this is multiplied by I1 to In as usual before plus IB at the end. So the size of this matrix now is becoming n plus 1 rows and n columns and 1 column. Whereas this is n rows itself. The rows are same, but then there is one additional column is there. So if I multiply again, it will be fine. Now comes the question, what is IB? So if I go back from this, if I write Ohm's law, the voltage here is Vk and the voltage here is Vj. So Vk minus Vj will be equal to Ib into Zb, right? Because since the Ib direction is from K to J, that means K is at higher potential compared to J. So therefore, this will be the voltage drop will be this. So, but what is Vk and Vj? So from this, so from this, I'll write Vk equal to, what is Vk? The kth, so let's say here it is Vk and here it is Vj. So Vk is nothing but the the kth row of original Z bus. So Z bus, I'll write it Zk row multiplied by I1 to In. So that is the one. And then the kth element of jth column. That means Zjk. So plus Zjk multiplied by Ib. So so this is what we are. I'm sorry, this is not Zjk. Uh, this is the kth row. That means Zkj minus Zkk. So this is the one, and this is multiplied by Ib. So I got the value of Vk. Now what is the value of Vj? So again from the above matrix I can write what is Vj. So Vj is nothing but Zj rho I1 to In plus Zjj minus Zjk into Ib. So these two are there. So let me put a line here. So I'll take a different color. So I have these two elements. Now that means I have this and this. So now if I just subtract Vk minus Vj, then I'll get what is Ib. Or in other words, I can write it like this. IbZb plus Vj minus Vk equal to 0. So I'm just writing it as a Ohm's law. So I have a 0 here. So I can actually write that 0 here and then add that uh, expression here. So, or in other words, let me not worry at this point. So what is 0? 0 is equal to IbZb plus Vj minus Vk. So in other words, what is this? So Vj minus Vk will be j minus k rho. So Zj minus k rho into all these currents, I1 to In. Now here IB is multiplied with ZB and then this terms. So here I have to reverse the sign. So I'll get ZJJ plus ZKK minus 2ZJK. So notice that JK and KJ both are same. And then plus ZB, this whole multiplied by IB I'm getting. So this is equal to 0. So I can write now the next step in this, that is V1 to Vn 0 equal to Z bus old, and then one column I am adding, that is Zj minus k column, and then here I am writing I1 to In, and then IB is the additional current, and for this I am getting Zj minus k rho and here ZLL, where ZLL is nothing but ZJJ plus ZKK minus 2 ZJK plus ZB. So this is just to save place, I have written ZLL notation. Now again you notice that there is a 0 here, so we can apply Kron's reduction. So simply by applying Kron's reduction, I can get the relation between V1 to Vn and I1 to In. So again apply Kron's reduction. So therefore Z bus new equal to Z bus old minus 1 by ZLL multiplied by Zj minus k column and then Zj minus k row. So this way by Kron's reduction I am able to get the final value of this one. So let us compare this formula. Of course this is also important. This is basically case 4. Let's compare this formula with what we had written here at the top. So this one, this is exactly same because old Z bus minus J minus K column, J minus K row and then 1 by ZLL where ZLL is this one. So this way all 4 cases I have derived. So, so basically what we have seen so far is the derivation of 4 cases. Thus, using Kron's reduction as mathematical tool, and of course using Ohm's law, we derived all 4 cases of building Z bus. So this Z bus building 4 cases we have just derived, and if you want to again refer, so you can always see this see these 4 cases summarized in one place, and with this we are going to get the idea about what are the 4 cases. Thank you.